There is a persistent myth that black holes are essentially giant cosmic vacuum cleaners, wandering through space and indiscriminately sucking up everything in their path. In reality, they only exert a normal gravitational pull for their mass. If our sun were magically replaced by a black hole of the exact same weight, Earth wouldn't be dragged into the abyss. We would continue to orbit it in the exact same path, though the planet would quickly freeze over. What makes these objects unique is their extreme density. A black hole forms when a massive amount of matter is packed into a microscopic area. This creates a curvature in spacetime so severe that the escape velocity becomes greater than the speed of light, about 300,000 kilometers per second. This diagram illustrates the Schwarzschild radius equation. It shows that any object in the universe can theoretically become a black hole if it shrinks past a specific mathematical threshold. They aren't magical anomalies or tears in reality. They're simply the extreme mathematical endpoints of mass and gravity. This animation shows a cross-section of a dying star. For millions of years, a massive star maintains a delicate balance called hydrostatic equilibrium. The outward pressure from nuclear fusion pushes perfectly against the inward crush of gravity. Deep inside the core, hydrogen atoms continuously fuse together to create helium, releasing huge amounts of energy. As the star fuses heavier elements, carbon, oxygen, silicon, and finally iron, it creates a fatal problem. Fusing iron absorbs energy instead of releasing it. The internal engine stalls, and the outward pressure holding up the star disappears entirely. With nothing left to push back, gravity takes over completely. The core collapses inward at astonishing speed, triggering a catastrophic rebound, a massive explosion known as a Type II supernova. When the dust clears, a dense remnant is left behind. If that remaining core is more than about 3 times the mass of our Sun, the inward gravitational crush continues completely unchecked, violently folding the massive dead star into a stellar mass black hole. This creation process represents the exact moment where gravity wins the ultimate cosmic tug-of-war against every other physical force. Because no matter, energy, or information can travel faster than light, anything that crosses the boundary of a black hole is trapped. So how do astronomers actually observe an object that gives off no light? We do it by watching what happens to the matter around it. Often, a black hole is surrounded by an accretion disk, a swirling vortex of gas, dust, and plasma. As this material spirals inward, friction heats it to extreme temperatures, causing it to blast out X-rays and radiation. We also look for gravitational lensing. The immense gravity of a black hole literally bends the path of light from stars sitting far behind it, causing those background objects to appear violently stretched or artificially brightened. And when 2 black holes collide, the impact sends literal ripples through spacetime, called gravitational waves, a phenomenon we first detected in 2015 using the LIGO observatories. While stellar mass black holes are scattered throughout the universe, much larger variants exist at the center of nearly every major galaxy. These supermassive black holes contain the mass of millions or even billions of suns. In 2019, the Event Horizon Telescope captured the supermassive black hole in galaxy M87, revealing glowing gas swirling around a dark void. 3 years later, they captured Sagittarius A star, the 4 million solar mass black hole anchoring our Milky Way, visible through brighter nodes of plasma. In both cases, we cannot see the object itself. We can only witness the violent shadow it casts upon the surrounding universe. That shadow marks the edge of the event horizon, the absolute point of no return. Here, the rules of reality are governed entirely by Albert Einstein's theory of general relativity. If you fall past this boundary feet first, the gravitational pull on your toes is vastly stronger than the pull on your head. This extreme tidal force stretches matter out into a long, thin shape, a physical process known as spaghettification. But space isn't the only thing that warps. Time itself is stretched. This animation shows time dilation. Time moves slower in stronger gravity, so a clock near the event horizon ticks drastically slower than one safely distant. To an outside observer, a falling object appears to slow down, fade from gravitational redshift, and freeze at the edge. But from the perspective of the object falling, time would feel completely normal as it plunges past the boundary. At the event horizon, black holes break our common sense, turning theoretical physics into a visceral, inescapable reality. If you survive the journey past the event horizon, you eventually reach the absolute center, the singularity. Here, the entire mass of the star has been crushed into a microscopic space, creating a point of infinite density. This animation represents the core crisis in modern science. To understand the singularity, we have to combine general relativity, which explains massive cosmic objects, with quantum mechanics, which governs the microscopic. But when forced together here, these two mathematical frameworks completely contradict each other. At this exact microscopic coordinate, our current equations and the known laws of physics simply stop working altogether. The singularity is a glaring error message in the human understanding of the universe. This brings us to the question of whether black holes last forever. Physicist Stephen Hawking discovered that they actually leak energy back into space over incredibly long periods of time, a process now known as Hawking radiation. This creates what scientists call the information paradox. If a black hole eventually evaporates into absolutely nothing, what happens to the quantum information of all the matter it ever swallowed? Is it permanently destroyed? While researchers don't have the answer yet, some mathematical theories suggest that this trapped information might flow through wormholes, theoretical tunnels connecting entirely different regions of spacetime. Black holes provide the extreme conditions needed to push the limits of gravity, time, and energy, functioning as the ultimate natural laboratories for the study of our universe. Reconciling the physics within the singularity may be our only path to finally discovering a true theory of everything.